Now that we've defined the dot product and what it means for two vectors to be orthogonal, we turn to a related tool that will be helpful in finding orthogonal vectors. The transpose of the m by n matrix A is the n by m matrix A with a superscript of T, whose columns are the rows of A. For example, if A is the matrix with columns 1, 5, 2, 6, 3, 7, and 4, 8, then the transpose of A is a 4 by 2 matrix, and its columns are 1, 2, 3, 4, and 5, 6, 7, 8. Some notation: when we specify an m by n matrix using its columns, we have been using the shorthand A is equal to V1, V2 down to Vn. If we transpose this matrix, then we use the shorthand A transpose is equal to the column V1 transpose, V2 transpose down to Vn transpose. So to see why the transpose is an interesting object, let's think about a vector with entries v1, v2 down to vn. We can think of the transpose of this vector, v transpose, as the 1 by n matrix with entries v1, v2 down to vn. So if we take any n-dimensional vector w, when we multiply v transpose by w, we'll get v1 w1 plus v2 w2 plus etc. plus vn wn, which we can recognize as the dot product v dot w. So we can think about the transpose as defining a matrix transformation from Rn to R. We'll denote this as v dotted with blank. It takes in a vector w, and then it multiplies w by the transpose of v on the left. And of course, if we think about this as a matrix transformation, then it makes sense to think about the null space. The null space of this matrix transformation gives us the set of all vectors that are perpendicular to v. For example, let's use this to find all the vectors that are orthogonal to the four-dimensional vector v with entries 2, 4, 6, and 8. So if we take the transpose of this vector, then we'll get the matrix 2, 4, 6, 8, and we can put this into reduced row echelon form by simply scaling the only row by 1/2. So we see that the null space is cut out by the single equation x1 plus 2x2 plus 3x3 plus 4x4 is equal to 0. We can solve for x1 in terms of the other three variables, and we can express this as a set of vectors with the first coordinate negative 2x2 minus 3x3 minus 4x4, and the other three coordinates simply x2, x3, and x4. So we can see that this is a three-dimensional subspace of R4, spanned by the three vectors negative 2, 1, 0, 0, negative 3, 0, 1, 0, and negative 4, 0, 0, 1. So if we take any vector from this three-dimensional subspace of R4, let's say w is equal to negative 1 times the first vector plus the second vector minus 3 times the third vector. Then we get the vector with coordinates 11, minus 1, 1 minus 3. And we can see that if we take the dot product of v with w, then we'll get 22 minus 4 plus 6 minus 24, which gives us 28 minus 28 is 0. So we can see that the set of all vectors, which are perpendicular to a given vector in R4, form a three-dimensional subspace. So if we're given a matrix A, which is an m by n matrix So there are n m-dimensional column vectors, v1, v2 through vn. Then we can think about multiplying the n by m matrix A transpose with an n-dimensional vector w, and we'll get v1 transpose w, v2 transpose w, down to vn transpose w, which is, of course, in each row, simply the dot product of v1.w, v2.w, down to vn.w. So combining this with our previous observation, we can think about how to find the set of all vectors that are orthogonal to a given set of vectors in Rn. So paired with our previous observation that the null space of V transpose is a set of all vectors orthogonal to V, we can see that the null space of A's transpose will give us the set of vectors W, so that V1 dotted with W, V2 dotted with W, all the way down to Vn dotted with W is equal to 0, is the set of vectors orthogonal to each of the V1, V2 through Vn's